A really common occurrence in physical systems is that there's like a moment of impact. Think about like a hammer hitting a nail. There's that moment of impact and it's over. Or a golfer swinging a club, or a baseball player hitting the ball. That impact happens for a very small amount of time, but it does a big thing. So we want to be able to describe that idea of this function being like on or off and it being really super impulsive in that way. That's where the Dirac delta function comes in. So today we're going to talk about that function and how we can take the transform of that function. So the first thing we're going to introduce is this idea of a unit impulse function. So we're taking a function like delta sub a of t minus t naught, where it's going to be equal to 0 when we're between 0 and t naught minus a, so some amount of time before this moment of impulse. And then it's going to be 1 over 2a for the impulse itself, so from t naught minus a to t naught plus a. And then after we get above that barrier of a, that buffer of a, it's going to be 0 again. Now, if we take the integral from 0 to infinity of this unit impulse function, it equals 1. That's why it's called the unit impulse function and not just an impulse function. Now, the Dirac delta function is a little bit of a misnomer. It's not a function, but it's a special case of this unit impulse function idea. So the function, or not a function, that approximates delta sub a of t minus t naught, and it's defined by the limit as a approaches 0. So we're basically getting so close that it's really instantaneous impact that we're looking at and then nothing on either side of it. That's what the Dirac delta function is doing. So it's defined just as delta, there's no subscript, of t minus t naught equals the limit as a approaches 0 of delta sub a with the unit impulse function deal of t minus t naught. So there are a couple of properties of this Dirac delta not a function. So it equals infinity when t equals t naught, and it's 0 everywhere else. Also, if we take the integral from 0 to infinity of it, then we get 1. So it's a unit impulse function setup. But remember we said that the Laplace transform of a function approaches 0 as we go to infinity. But here we have the Laplace transform going to 1 because it's a constant function. So this is something that tells us this is a weird function and it's not a function. All right, so if we want to take the transform of the Dirac delta function for t naught greater than 0, so some unit or some instant when we're going to have this impulse happening, we're going to take the Laplace transform of it, and what we actually end up with is e to the negative s times t naught. That is the Laplace transform of this. So let's take a look at an example. We'll look at an initial value problem that's actually a second order differential equation, so it's got two initial values. So using what we know about the Laplace transform and this new theorem that we've just added, the Laplace transform of our differential equation is going to be s squared capital Y of s, which is the Laplace transform of y, right? Minus s plus capital Y of s. And it's going to equal 4 times the Laplace transform of our Dirac delta function that we have here. And we just learned in our theorem that this is going to be e to the negative s times our initial instant time, which in this case is 2 pi. So then all we have to do is solve for y of s. So I'll get everything that's not y of s terms on one side and y of s terms on the other side. So we've got s plus 4e to the negative 2 pi s. And we'll factor out a y of s times s squared plus 1. And then divide by our s squared plus 1. So we get y of s is going to equal s plus 4e to the negative 2 pi s all over s squared plus 1. So now I'm going to pull this apart into two fractions. So this is really s over s squared plus 1 plus 4e to the negative 2 pi s over s squared plus 1. The first part of this is obviously cosine of t, the inverse Laplace transform. The second part, I need to use my second translation theorem. I'm going to use the unit step function, or that heaviside function that we had, and I'm noticing that it's shifted by 2 pi. So it looks like sine, except it's been shifted by 2 pi. So this is actually going to end up being our cosine of t plus pulling the 4 out in front, and then noticing that it looks like sine of t minus 2 pi. It's been shifted by 2 pi, and then we have to multiply by that unit step function of t minus 2 pi. So this is again when we were looking at translating on the t-axis that we found this. Now, in general, we try not to leave trig functions, especially with 2 pi's in them, because 2 pi's like the period of trig functions. So sine of t minus 2 pi is the same as sine of t. And remember, the unit step function deal is basically turning this off and on. So sometimes it's going to show up and other times it's not. Namely, it's not going to show up until we get above 2 pi. So I can rewrite all of this as a piecewise function. It's a little bit nicer to look at, knowing if y of t is going to equal, cosine of t is there regardless. That's outside of this shifting thing that happened. And when we are between 0 and 2 pi, this unit step function hasn't kicked in yet. So this has not been turned on. This part's not there yet. But after 2 pi, so 2 pi is less than t, then it's turned on and we end up with 4 sine of t added in. So this is how we take the transform of a function that involves the Dirac delta function. We're solving a differential equation that involves a Dirac delta function using the Laplace transform and then taking the inverse transform. And some of you might be wondering, whatever happened to those initial conditions that we had? Well, I kind of breezed through that part and we didn't actually work through how did we get from here to here. And that we used those initial conditions in. And so that's the deal here. All right. So if you are struggling with that or having some questions about, then go back and take a look when we were looking at solving differential equations using the Laplace transform.